Hello, in this video we're going to go over some other properties of limits and continuity. So here is the first theorem. Let D1 and D2 be subsets of Rn and Rm respectively. Let f from D1 to Rm and g from D2 to Rk be two functions. Let a be a limit point of D1 and a limit point of the domain of the composition. Suppose f of x approaches b and g is continuous at b, then composition of these two functions approaches g of b. Okay, so let me first start with what the theorem actually says, and then we'll go over the proof. So we have a function f from d1 to rm, and then we have a function from d2 to rk. Now, what does this theorem tell us? It tells us that if you take a point A that is a limit point of D1 and f of x as x approaches A approaches B, and then you take the composition of these two as x approaches A, it would approach to g of B. This is assuming that g is in fact a continuous function. So why does that work? Okay, so let's write down the definition of limit and then see what we have. So by assumption, we have these two limits. By assumption, limit of f of x as x approaches a is equal to b, and since g is continuous at b, limit of g of x is equal to the value of the function g at b. Again, that's by definition of continuity. Now, what are we trying to prove? We are trying to prove that when I take the composition of these two, limit of the composition of g and f as x approaches a, I end up with g of b. So I want to show that. Let's write down the definition and see what we need to show. So we need to show for every epsilon positive, there is a delta positive that whenever the distance between x and a is less than delta, more than 0, and x is in the domain of, let me put it this way, d sub GOF. This is the domain of GOF. Then the distance between f of x, GOF of x and g of b is less than epsilon. Okay, so this is what we're trying to show. So how do we show this? So we're going to have to start from epsilon positive, and then we're going to have to come up with delta. Okay, so what do we need to do? We need to show that g of f of x approaches g of b. Now we know that the limit as something approaches b of g of that would be g of b. So we're going to have to use continuity at point b for g first. So let epsilon be positive. Now there is some positive delta such that if x is in the domain of g, and let's call that maybe y to not mix it up with the x here, because this is actually not in the domain of f, it is in the codomain of f. When y minus b minus b is less than delta and more than 0, then g of y minus g of b is going to be less than epsilon. Okay, so now I want to replace y with f of x. Now we'll take that delta. So by definition of limit again, there would be some delta 1 positive such that anytime x is in d1 and x minus a is less than delta 1 greater than 0, then we can get that the distance between f of x and the limit, which is b, is less than delta. So my epsilon here is like basically delta. So what does that give me? If I look at this inequality here, I know that this implies g of that minus g of b is less than epsilon. So I'm going to call this a star. This implies by star that g of f of x minus g of b is less than epsilon by star. And what does that tell us? It tells us exactly, so let me write it down. As long as x is in the domain of GOF. Why? Because I need to be able to evaluate this one. So the condition here was y would have to be in the domain of G, which is the same as saying x is in the domain of GOF. So what does that mean? Therefore, what we just showed is that the limit of GOF of x is in fact g of b as x approaches a. And that's exactly what this theorem stated. Okay, let's look at the next theorem. So the next theorem allows us to use some properties of limit, which is limit of sum is sum of limits, and limit of product is product of limits. So in order to do that, you could either use epsilon delta directly, or you could use the previous theorem and the fact that sum and product are in fact continuous functions. So consider these functions. Consider sum from R2 to R and product from R2 to R given by, these are functions that we have shown before that they are in fact continuous. X plus y, and product is just x times y. Now we know that these two are both continuous. We know S and P are in fact continuous. So if we know these are continuous, then when you take the limit, so let's take the limit of, so I want to take the limit of this sum. So this sum can be written as f of x plus g of x can be written as s of f of x comma g of x, because that's basically just the sum. Now, what do I know? I know that s is a continuous function. So if s is a continuous function, I can apply the previous theorem. But first, I'll have to find out what's the limit of this guy. So if I take the limit of this, limit of f of x comma g of x, by component-wise limit as x approaches a, this would be, so we know that the limits at a exist for both g and f. So this would be the same as the limit of f of x comma the limit of g of x. This was a theorem that we proved, that to find the limit of a function, you could just find the limit of each component. Now, since S is continuous, when you take limit of S of f of x comma g of x, you would get, as x approaches infinity, as x approaches a, you get S of limit of these, limit of f of x comma g of x, which we know as x approaches a, which we know it is S of limit of f comma limit of g as x approaches a. And what is S of something? It's just the sum by definition. So this is limit of f of x plus limit of g of x as x approaches a. Okay, so the second part would be very similar. So if you look at P is also continuous. Since P is continuous, we can write it down as limit of product of f of x and g of x as x approaches a. So this guy is exactly f of x times g of x. Same way that the previous one was f of x plus g of x. So since we know this is continuous, we can swap the limit and the function. This would be product of limit. And then limit of component becomes components of limit. So this comma limit of g. And what is p of something? P is just a product. So this would be just limit of f of x times limit of g of x as x approaches a. So what we got is limit of product. So that tells us that limit of, so if you look at here, this highlighted one is limit of product. So limit of f of x times g of x as x approaches a. And that equals the other side. And the other side is just the product of limits, is equal to limit of f of x as x approaches a times limit of g of x as x approaches a. And that completes the proof. And the previous one was also almost identical to this. It would be limit of sum equals sum of limits. Okay, so now the next theorem, I won't really go over the details of the proof of this one. This is not going to be very easy. Every single one of these functions has to be dealt with separately. But I'll briefly tell you how we can deal with them. So all of the following single variable functions are continuous over their domain. Polynomials are continuous. Why is it that polynomials are continuous? Because a polynomial can be obtained by adding and multiplying. We know that x is continuous, so if you multiply x a bunch of times, you get x to the power of n is also continuous. We know constants are continuous, so you can multiply it by a constant and you can add them. So that way you can get all the polynomials. Root functions are continuous. That's a little bit different, so you have to do it separately. Rational functions, polynomial over polynomial, are continuous. Trigonometric functions, their inverses, these are all continuous. Exponential functions and their inverses are all continuous. So these all are all continuous functions, and we really won't be able to go over the details of the proof. That's a whole different story. So it's not very every one of them is going to be time consuming. Okay, so let me do one more example here. Prove that the function f from R3 to R2 defined by that is continuous. So we had a theorem that if you want to check a function is continuous, we will have to check each of the components is continuous. So by a theorem, f is continuous if and only if each component is continuous. So in other words, I'll have to look at these functions, g from R3 to R2, or let me actually just R to R. Let me just call it f1. That's the first coordinate function. f1 of x comma y comma z is equal to x plus y. f2 from R3 to R is given as f2 of x comma y comma z equals sine of xy plus cosine of z. So if I show both of these two functions are continuous, then the function would be continuous. So what we're going to do is we're going to write down f1 as a composition of continuous functions, because by the previous theorem, if you have two continuous functions, the composition would be continuous. So let's write down f1 of xyz as a composition of functions. So here's now how we can do that. Okay, so this is f1 of xyz, and I want to write that down as a composition of functions. So first I'm going to extract x and y. So how do we extract x and y? We can extract x by doing pi 1, which was the projection onto the first component. So pi 1 of x, y, z gives me x. I would like to add them. So I would like to add the first component and the second component. So as you see, this is going to be x, this is going to be y, and this whole thing would be x plus y. Now this function is exactly the same as f1. It's a composition of a bunch of functions. So let me argue this. Pi 1 is continuous by an example. It was an example we did earlier in the previous video. Pi 2 is continuous, again by an example. Thus, pi 1 comma pi 2 is continuous by a theorem, because if all of the coordinate functions are continuous, then the original function is also continuous. S is continuous, thus the composition S of pi 1 comma pi 2 is continuous. Okay, so that gives us the first coordinate function. The second one, we'll have to look at this one, show this is continuous, and then the sum is continuous. We know product is continuous, we know sine is continuous, so we're going to just do that. So f2 of xyz is equal to, let me just rewrite it first, sine of xy plus cosine of z. Okay, so first it is a sum, so it's a sum. The first one is sine, which is a continuous function, of product of x comma y, but the domain of the function was xyz, so I'll have to first project it. So it will be pi 1 xyz comma pi 2 xyz. So this is y, this is x, this is xy, so that's sine of xy, so that's what I got, and now I want to add them. Now I have to do cosine of, well, z is the third component, so that's pi 3 of x comma y comma z. This function is continuous for the same reason. So you'll have to write down the details of why, but it's very similar. Because pi 1 is continuous, pi 2 is continuous, therefore this one is continuous, pi 3 is continuous, product is continuous, sine is continuous, composition of continuous is continuous, therefore this is continuous, cosine is continuous, therefore this is continuous, and then if you take two components that both are continuous, you get a continuous function. Compose that with s, you get another continuous function. So this is also going to be continuous. Okay, and here's the last thing we're going to do in this video. Every polynomial is a continuous function from Rn to R. So if you take a polynomial, we want to show that it is a continuous function. So what is a polynomial? It is a sum of product of these variables. So you take x1 through xn, and then you look at a sum, some coefficient, and then x1 to some power, let's say alpha 1, x2 to another power alpha 2, xn to another power alpha n, and then these constant coefficients are real numbers and they would depend on the exponent. So this would be sum, let's say c sub alpha 1 through alpha n. So we want to show that this is continuous. So why is this continuous? Well, you could do it by induction on the number of terms, but briefly, so I won't go over the details of that, but briefly, this is continuous because you can write that down as a product of a bunch of continuous functions, and we know that product is also continuous. So for example, if you have x1, x2, x3 squared, and this is your polynomial, if your polynomial of x1, x2, x3 and x4 is this polynomial, then the way you can deal with that is to say, well, this is product of two terms, x1, x2, and x3 squared. So one of them would be x1, x2, which is itself a product. So we'll have to do pi 1 of x, let me just call it x, comma, pi 2 of x. This would be x1, this would be x2, this would be x1 times x2. Then we'll have to multiply that by x3 squared. So this would be product of x3 and x3. So this would be x3, this would be x3, and this is x3 squared. And when you multiply them all, you get x1, x2, x3 squared. If you have a constant in front, the constants are also continuous. That's pretty easy to check. And therefore, and by the way, I probably need to name the polynomial something different. Let me just say f, because I have p for product. And that was fine. Yeah, so then I get something that is continuous. Okay, so next time we'll talk about the topology of Rn. I will see you in the next video.